So the question tells us complex number W is given by 1 plus 2i. Alright, so W equals 1 plus 2i, and part 1 asks us to find W cubed in the form of x plus yi, showing our working. Note that this isn't an nth root of unity question. It's a simple expansion question because it's only 2 marks. Alright, so we'll only have to cube the 1 plus 2i since they ask us to show our working explicitly. So we'll be careful not to skip any steps. Alright, so first I'll write out the basic expansion. I'll expand 2 brackets first. Here I'll have my a square plus 2ab plus b square. Then I'll do my final expansion. Alright, 1 plus 4i minus 4 plus 2i minus 8 minus 8i. And by simplifying, I'll have my final answer, negative 11 minus 2i equals to w cubed. Something to note is that many questions in paper 1, almost all of them, can be counter-checked using your GC. So if we use our GC here, alright, we can type in our w, which is 1 plus 2i. Alright, then we can cube it, and GC will tell us the answer. So we can always make sure that our answer is correct. Now moving on to question 2, after we get our w cubed. Okay, so for part 2, given that w is a root of this equation, this polynomial equation, find the value of the real numbers a and b. So whenever you have a polynomial equation, it's always a good habit to first call it fz at the start. So if fz equals to az cubed plus 5z squared plus 17z plus b, alright, now we note that all the coefficients in this polynomial equation are real. So we can conclude, since all coefficients are real, alright, and we know that one of the root is 1 plus 2i, so the conjugate of w, which is w conjugate, will also be a root. So the conjugate is 1 minus 2i is also a root. Alright, not to be confused with factors. Okay, so since we know that this is a root, next they ask us to find the real numbers a and b. So one easy way to find this is to sub in the root. Alright, so we can either sub in 1 plus 2i or 1 minus 2i, both will do. Alright, so for example, if we sub in 1 minus 2i, if we sub in 1 minus 2i, okay, then we will have a 1 minus 2i cubed plus 5 1 minus 2i square plus 17 1 minus 2i plus b. Sorry, I made a mistake there again. Okay, so what I did was substitute all the z with the root of 1 minus 2i. Next, we can expand this. There's no need to expand it manually. We can use our GC to expand this. For example, 1 minus 2i cubed, alright, can be done using GC. 1 minus 2i cubed, GC will expand it for us, negative 11 plus 2i. Okay, so we can do the same for the square here. So expanding the 1 minus 2i square, we will have negative 3 minus 4i plus 17 minus 34i plus b. Alright, next step I'll just do basic expansion, which is opening up the brackets. And the rest I'll just copy it. Okay, now something to note is that this is our factor theorem. Okay, if we sub in the factor, it will equal to 0. So since the left side is equal to 0, what we can do is we can group all the real numbers together and all the imaginary parts together. Then we can equate the coefficients to 0. So first thing we want to do is sieve out all our real parts, which is negative 11a, negative 15, plus 17, and plus b. So 17 minus 15 will give us 2. We still have the minus 11a and plus b for our real part. For the imaginary part, we have plus 2ai, minus 20i, and minus 34i. So in total, we have 2a minus 54i. Alright? Since the whole thing equals to 0, our real part will equal to 0, and our imaginary part will equal to 0. So now it's sort of like solving a simultaneous equation. Real coefficient will equal to 0, and your imaginary coefficient will equal to 0. From the imaginary coefficient, okay, equation 2, we can see that 2a minus 54 equals 0. We can immediately solve that a will equal to 27. If we sub that into equation 1, we'll have 2 minus 11 times 27 plus b equals 0. We can also very quickly solve for b, which will equal to 295. Alright, so that's for part 2. Now we move on to part 3. Okay, using these values of a and b, find out the roots of this equation in the exact form. So now we know values of a and b, so we would like to rewrite our fz as subbing in all the values of a and b. So fz will be 27z cubed plus 5z squared plus 17z plus 295. Alright, since we already know two roots, one is 1 plus 2i, the other is 1 minus 2i. So we can write it in the form of two roots already. So now we write out the factor, which is z minus the root 1 plus 2i times z minus the second root 1 minus 2i. Okay, since we know the coefficient of z cubed is 27, coefficient of z cubed is 27, z times the third z must give a coefficient of 27. So I'll add in a 27 as the coefficient here. Alright, and this must be a real root, since we already had a pair of imaginary roots. Alright, so I'll introduce k, where k is a real constant. Okay, next what we want to do is expand these roots out. So what we do is first open up the bracket. We will have z minus 1 plus 2i here, and 27z minus k. Okay, here we can treat our z minus 1 as a, so we will have a minus b times a plus b. So this is our difference of square formula. So we can have z minus 1 squared minus 2i bracket square. Okay, and here we will still have our 27z minus k. So by expanding this, we will have z squared minus 2z plus 1 plus the 4 from the 2i square. Then I'll copy the rest. Now we simplify this quadratic factor, and we will have z squared minus 2z plus 5 times 27z minus k, and this whole thing still equals to our fz. Okay, up to this step, there are two ways that we can proceed. One is by doing long division. We can take our fz to do long division against this z squared minus 2z plus 5, and we will have our final linear factor. The other way is by comparing coefficients. In this case, I'll use comparing coefficients because it's faster. Okay, since we know that 5 multiplying by negative k will give our constant term in fz, right? This is the only multiplication that will give our constant term. So we know that 5 times negative k will equal to 295. So from here we can get that k is negative 59. Okay, so here we know that the last factor is 27z plus 59. So to find the roots of the equation, that's what the question is asking for, all the roots of this equation. Since the factor is 27z plus 59, We can now list out all the roots of the equation. The roots are, first one is 1 plus 2i, second one will be the conjugate of 1 plus 2i, 1 minus 2i. The final root will be equating the factor to 0, so we will have negative 59 over 27. So that's it.